Okay, so I wonder slash worry about what you're going to think when I tell you about what we're going to learn about right now. Because we're going to be learning how to count, and you maybe justifiably might tell me, Sean, what on earth? I have been counting since, I was this high since I was very, very small. Why are you trying to teach me how to count? Well, this time I'm not going to give you too much preamble. I'm just going to kind of spoil the surprise with an example. And really, I just want you to keep in mind that we have three situations in which maybe it's more difficult to count than you might think. And I'm going to really tell you about how to go about approaching the problem in those cases. So we start with, let's say, just three objects. So we have a pink ball, we have a yellow ball, and let's say we also have a just a little teal ball here. So a pink ball, a yellow ball, and a teal ball. My apologies if anyone's colorblind, but I'm also going to number them as ball 1, 2, maybe outside. I'll number them as ball 1, 2, and 3. Okay. And the question I'm going to ask is, how many ways can I order? So can I order uh, these three distinguishable, and I'm going to change color for this, the distinguishable uh, objects. So that's all I'm asking. It's a simple enough question. How many ways can I order them? Well, let's kind of go ahead and figure it out. So let's not kind of bother about the colors, but we'll just say, well, I think you can see that we could order them as 1, 2, 3. So we could have the 1 first, or we could have 1, 3, 2. So these are all the ways with 1 first. Okay. And let's try the ways with 2 first. So you could have 2, 3, 1. But of course, there are only two other things. So the only way to order those would be 2, 1, 3. And these are all the ways with 2 first. And finally, let's start with a 3. And I'm going to say 3, 1, 2. Well, of course, I think you get the game by now. The other way to order them is we have 3, 2, 1. And these are all the ways with 3 first. Okay, so it seems like the answer is 6. The answer, 6, right? And it's like, well, that's fine, but what? You've not really taught me anything interesting there, Sean. Let's just investigate this answer a bit more carefully, because I see that the answer 6. It seems like 6 seems to kind of speak to me as an answer that might make sense, but let's try to dig in and figure out where that 6 came from. So let's say why. Well, the answer is, when I pick the first ball, there are 3 ways to pick it. So there's 3 ways to pick the first ball. So ways to pick ball 1. Okay, so this is in an ordering. Okay, and for the second ball, how many ways are there to pick it? Well, you've already used one ball up, so there are only 2 left. Okay, so there are 2 balls left in your bag of 3 balls. So there's 2 ways to pick the second ball after you've picked the first one. So this is the number of ways to pick ball 2. Maybe we should color these the same color as the ball. So we have pink, yellow, and teal. So we have pink is the number of ways to pick ball 1. and we had this nice little teal color here to pick ball 2. Seems reasonable enough. How many ways are there to pick the final ball? Right, remember this is a string of 3 balls and we're trying to order them. We've used one of the ways to pick the first, we've used one of the ways to pick the second. Well, if we had 3 balls to start off with and we've chosen where the first 2 go, there's only going to be one way to place the last ball. So this is the number of ways, and I think I've botched this because I think you were meant to be yellow, not teal. My sincerest apologies there. So you were meant to be a yellow, which frees us to use teal for the color for the final ball. So this is ways to pick ball 3. So all I've done here, is I've said, look, we started off with 3 balls and we're just counting how many ways to do it. And let's see what we get. Well, we got 6, right? We got 6, which was in what we got before. So we got agreement. Okay, so this way we've kind of counted it 2 ways. We counted it directly. So counted directly. And here we've kind of sketched the way to kind of count. Let's see, how can we describe what we've done here? So what we've done is we just reasoned about how many balls could go in each slot. We counted by reasoning. So counted by reasoning. Okay, and this reasoning is what's going to help us because we have insight into how it goes. Because I think you can probably see is if I have n balls, so I have n balls, so n is any number, well, the number of ways to do it would be n times, so let's start off. So suppose I have, and let's make that a bit neater, and let's just change the color so it stands out a bit. I have n balls. I have n balls. How many ways can I order them? Well, there are n ways to pick the first, and I've used the first, so there's n minus 1 left to pick the second slot. And then, of course, there'll be n minus 2 to pick the third slot. And you'll just keep counting down like this and multiplying together until you get down to 2 and then finally 1. So in general, you kind of see the pattern here. You just multiply them all together. So the answer is, another way to write this is you write this as n factorial. So n with an exclamation mark. What that means is you take this and you start from a number and you just keep counting down. So for example, I think you understand that 5 factorial has just got to be 5 times 4 times 3 times 2 times 1. And if you kind of multiply them all up, you get 120 would be a result. Okay, very good. And this is a result that by the way, we really do want to box this up. We want to box this up and be quite careful to say this is an important result. So this is the answer to the question. How many ways can I order them? But this also has a name that we call this the number of permutations of n objects. So if I have n objects and I want to order them, any particular ordering is called a permutation. And what I've counted here is the number of such permutations. So let's pick a color scheme and stick with it. So we're going to, let's yellow for this equation. And here, I've said this is called the number of permutations. So this is permutations. So we're counting the number of permutations of n objects. And this is our first result. And I think you can see the utility of this and why maybe it's worth spending some time thinking about counting now, because this works for any number. So I've just shown you here another example. If I had 5 balls, there would be 120. And you might think, well, there were only 6 before. Why has it jumped up to 120? Well, you'll soon learn that factorials grow very, very quickly indeed. And that's part of the reason why counting becomes difficult, because in many of these situations you end up with really fantastically large numbers. But saying that, let's kind of move on. We've done our first problem. We've counted how many ways to, how many orderings or permutations there are of n objects in general. So let's start somewhere else. So again, this time we have some balls, but this time we're going to have, let's say we have a pink ball for our first one. Let's say we have our peach for our second ball. We have yellow for our third ball. Let's kind of use some cooler colors here. So we have our teal again, or kind of light blue. And here we're really going to have our kind of a darker blue. And again, this is going to be difficult for the colorblind people. Maybe I'll kind of move this around. But I think the point is, really we can replace these with numbers. So I'm going to say 1, 2, 3, 4, 5. So it doesn't really matter. And my question is, how many orderings, or how many ways can I select? How many ways can I select? And I'm going to pick a specific number. I'm going to pick 3. So how many ways can I select 3 balls and then order them? Right. So what I'm saying is I started off with 5 balls. I want to know how many ways can I select 3 balls out of this, and let's kind of calm this down to 4, and let's say this is 2, because I think you probably have gathered that we'll be here forever if we're trying to enumerate that many. So how many ways can I select 2 balls and then order them? That's the question I'm trying to ask. Okay, so what are the, well, how many ways can I let's think about this. Let's say no, I think it's better. Let's say 2. 2 is kind of the most interesting way to do this, and we won't be here all day. Well, I think you can see there's kind of a bit of ambiguity here, because I can pick 1 and I can pick the 2. Of course, I can reflect that, so I can also get the 2 and the 1. Remember, this is how many ways can I select 2 balls, but I didn't say which 2 balls, right? So I could also have, for example, 1 and 3, but I could also have the flip of that. So the flip side of that would be 3 and 1. Of course, maybe I have ball 1 and I have ball 4, and of course I'm allowed to flip that, so I get 4 and 1 as well. Okay, so these are all the orderings starting with 1 and their mirror images. Okay. So very good. Now, what else? Well, I want to see the one starting with 2. So I think 2 and 3. Well, of course, that generates 3 and 2. I could have 2 and 4. Of course, that's just going to generate 4 and 2. And I think that's kind of it. But now we're going to look at ones starting with 3. I think this is it. I think, yeah, no, we're not. We've got 3 and 4. And of course, we can also generate 4 and 3. And if we count them, we have 6 here, we have 4 here, and we have 2 here. So the answer seems to be 12, right? The answer is 12. We have 12 ways that we count that we can order these numbers. And if I kind of just circle these to kind of just really make it obvious what I'm really counting. I'm actually counting all the distinct ways to choose two balls and order them. So these are all the possibilities for picking two balls, and of course there are two orderings because there are two ways to do it. Now this is kind of, again, this is the direct counting, so counting directly. But we want some insight. We want to know why this is the case. So let's have a little think about it. Well, if we think carefully, what are we doing? Well, we started with 5 balls. So let's see why. So we want to know why. Well, we started with 5 balls, so there's 5 ways to pick the first one. And how many do we have left in the bag? Well, we have 4, so there's 4 ways to pick the second ball. And how many do we have left? Well, there's 3 ways to pick the next ball. Now, let's kind of, again, this is, I think you'll kind of, oh, again, please excuse me, because we had 4 balls, so it's 4 times 3 times 2, please excuse me. So this is 6 times 4, which is 12. That is correct. But I want more insight than that. So what I'm going to do is, if you're thinking like a mathematician, this kind of, again, what have I done? Sorry, that's 4 times 3, which is 12. Please excuse me. But if you look at this, it's kind of screaming for something. 4 times 3 is 12, but 4, so there's 4 ways to pick the first ball and 3 ways to pick the second. Well, there's 4 ways to pick the first and 3 to pick the second. But this is kind of crying out to have more factors introduced. It's crying out for me to put in a 2. And I think after that, it's crying out for me to put in a 1. And you're kind of building up 4 factorial here. Now, of course, I'm not within my rights to do that in any general mathematical expression. If I want to do that, I'm going to have to build it up in the denominator. So let's, I think, maybe if we exchange colors here, I want to build up with the 2 and then the 1. So I think I'm going to, and let's kind of just to make this a bit nicer. I'm gonna say, let's make these teal. So let's make these teal. So you have 4, and you have a 3 here, and you have a 4 and a 3 here. You're multiplying them. But I think, remember, we need to fix this. So we need to divide by the 2 and the 1. We need to divide those numbers out. So we need to divide out the 2, and we need to divide out the 1. And now we still have our 4 times 3 because just as much as we've kind of inserted these numbers in, we can still cancel them. We're within our rights to just cancel, and we'll be back to our 4 and our 3. Okay, we'll be back to our starting point. But you can see now there's kind of, it's a bit prettier because the top, look, that's just 4 factorial. And on the bottom, that's just 2 factorial. Now, 2 factorial. Now, is that the 2 that we picked, or is that the 2 that we didn't pick? Well, if we think about it, it has to be the 2 that we didn't pick, okay? It's the 2 we didn't pick because we are dividing out all the permutations of the rest of them. See, we're trying to count how many ways to permute the 2 that we've picked, and then we do not care how many ways we can permute the other ones. There are 2 left, and there are 2 factorial ways to permute them. So we want to divide out all the ways to permute the others. So really, this isn't just 2 factorial, it's 4 divided by 4 minus 2 factorial. And I hope you see the distinction I'm trying to make here. The distinction is I'm not after the 2 that I selected. No, I'm trying to divide out the 2 that I didn't select, okay? And this leads us to our kind of more general result. We say, suppose I have, let's say, k objects. Let's say n. Let's say n. We have n objects. I want to ask how many ways can I select, and how many do I want to select? I want to select k of them. how many ways can I select k of them and order those selections. So two distinct things. We select k of them, and then we ask how many ways can we order them. Okay, so we want to do both at the same time. And in general, I think you can see the answer is going to be n factorial divided by n minus k factorial, because we're removing the ones that we're permuting so that we're left with the ones that we're not permuting. And there's a nice special symbol for this actually. We write npk. Okay, so we write npk, and the coloring used was this kind of pink here. We used this pink for the border, and we used yellow for the smaller border here. Very good. So this is the formula, and this is the kind of wording. And again, I think you can see that this is, this is the same as what we got before. It might seem like it's a waste of time and it's a bit more verbose than necessary, but really what we've learnt here is why the numbers are that way, okay? The numbers are that way because what we're doing is we're counting all the permutations of all four of them. Then we're dividing out the permutations of the ones that are left, the ones we don't care about anymore. Okay. And we have one more problem that we kind of frequently find in probability theory when we need to count. So of course, I think it should go without saying that the reason we're talking about counting is because if you want to calculate probabilities, you often have to count very large sets. And we say, okay, so I'm going to say, suppose I have, some balls. Let's say this time we're going to have 5. So we're going to have we'll have 5 balls, so the first one's going to be pink. The second one, let's say it's going to be yellow. Let's say the next one's going to be kind of like this teal color here, just trying to really lean in so we get some darker tones so we can distinguish these more sharply. We have our blue here, and finally we have our purple. We have our purple here. Okay, so we have 5 balls, and they're numbered 1, 2, 3, 4, 5. Okay, and my question is, what am I asking? How many ways can I select, let's say, 3 balls? And I'm going to be very clear about this, irrespective of order. Now, this is quite different to the questions we asked before and related to the most recent question we asked, because what I'm trying to figure out is how many ways can I just select 3 out of 5? Okay, so I have a bag of 3 things. How many possible so I have a bag of 5 things. How many handfuls of 3 things can I possibly arrange for? I think you kind of get the program now. We're going to figure out all the possible ways to draw 3 objects. So we're going to have 1, 2, 3. Well, we're not going to reorder them because, of course, we don't care about the orderings. We just care about the set. And we have, let's say, 1, 2, 4. I'm going to be very careful here because I'm likely to make a mistake. And I'm going to have 1, 2, 5. And notice the ordering guarantees I keep them unique. Okay. So again, that's fine. I'm going to say 1, 3, 4. I'm going to have 1, 3, 5. And next I'm going to have 1, 4, 5. And that's the last one. Well, we'll look for the one starting with 2 this time. So we have 2, 3, 4. We have 2, 3, 5. And I think we have 2, 4, 5. And I think we're done with the one starting with 2. And finally, we're going to have the 3, 4, 5. And I think that's all of them. Have I? Let's see. Have I messed something up? Ooh. Nope, that's absolutely correct. So here we've got 9 or 3 plus 1 plus 3 plus 1. And again, I want to be clear that each of these is a different selection. Each of these is a different selection. So each of these is a different selection, and there are 9 of them, just to be clear about what I'm saying. And here what we've done is we've counted directly. So we've counted directly, and we can see clearly the answer is 10. But again, we want some insight. We want to know why on earth is this 10? Well, I think I'm not really going to labor the point too much, but the idea is I alluded to it before, but the answer to this question is related to the answer to the first question. So why don't we start there? So the answer looks like it would be 5 factorial divided by, well, we're dividing out all the ways to permute the rest of them. And how many are left? Well, 5 minus 3, so that's 2. You have 2 factorial, okay? And I left some space, so you might be wondering what I'm going to put there. Well, this is the key. We don't care how to order the 2 that we left over, but we also don't care how we order the 3 that we selected. So we need to divide out those permutations as well. And again, just to kind of be a bit obtuse and a bit fastidious, we're going to write this as 5 minus 3 factorial times 3 factorial. Okay, and this is our answer. This is why this is kind of the way it is, because we're dividing out all of the permutations of the 3 we selected and all the permutations of the 2 we left behind. We don't care how to permute these because they're left over, and we don't care how we permute these because we don't care about how they're ordered, right? We just care about what's in the actual bag itself. So now we're ready to state the result that we just worked out. So we say, how many ways to select k objects from n objects. And this is called, in general, it's called the number of combinations. So we're asking combinations. And that's combinations of k drawn from n. And if that seems confusing, all I'm saying is I started with n objects and I drew k of them, and each of these bags, where we don't worry about the ordering, is called a combination, okay? And the answer is, well, it's equal to n factorial over k factorial times n minus k factorial. And again, we have a special symbol for this. It's called n choose k, so n with a c and k. And you probably guessed that the p here, maybe some people say it out loud as n perm k, okay? So all very good. So kind of our pinky color on the outside, or orangey kind of peach color, and we had yellow on the inside, I believe. So we had yellow on the inside. All very good. So I think we're happy now. So these are our 3 results. Very, very useful. Maybe it's worth just decorating this a bit more, because really I just would like to just take a moment to say that this is, of course, the number of permutations of k things drawn from n. So here we would say this is the number of permutations. This is the number of permutations of k objects drawn n object. So we start with n, we take k of them, and this here, the npk, was how many ways can I order them, and nChooseK is how many ways can I select them, but I don't care about ordering.